Morning students, we'll start with our today's lecture. So basically unit 4 has two chapters. So first we had completed, that is virtualization. Next chapter, that is chapter 8, is multiprocessor system. Multiprocessor system, so these are the three bifurcations which are given to your whole computer system. That is, multiple means many, processor means on which whole your process is going to work, and systems means when you connect those all multiple systems to one processor or many processors to one single system, how that vice versa scenarios are going to work out, that will be seeing in this chapter. So first, what is multiple processor system? So there are three scenarios of multiple processor systems: a shared memory multiprocessor, a message passing multi-computer, a wide area distributed system. So first is a shared memory multiprocessor. We'll see that. Suppose if computers are small in size, then heat dissipation problem needs to be faced. Heat generation is directly proportional to speed of computer, and for smaller computers getting rid of heat is difficult. So basically when we talk about a shared memory, what happens is, if a computer is small in size and if the heat generated because of it, there is a fan inside a system, but the heat generated is equal to the how fast your computer is running, and because of which, if the computer memory is small in size, it requires a lot of cooling factor, and which is not possible, and therefore getting rid of such heat is difficult in small computers. Massively parallel computers have more CPUs in it, each running with normal speed but collectively having huge computing power. So when parallelly the memory is shared, that means n number of systems are working together, because of which they have that computing power, but then still they, even if they run in a normal speed or they have that collective all the capacity, still the heat generated is very large. For very large size applications, very huge data processing is required, and parallel computers are good options. So for this, parallel computers can be a good option, as any independent and unrelated computers are spread worldwide. Communication between them is through message passing. So what happens is, through this, for parallelly running, parallel means at the same consistency all the systems are running all together. Therefore more work is carried out under interconnection technology, and different interconnect technologies resulted in collectively different kinds of system and different software organizations. So there is a lot of scope in your organizations because of these parallel computer technologies. Many number of CPUs, say 1000, can share a common memory and use shared memory for communication. So sharing of memory nowadays is a very big crucial part of the organizations when they are working as a part of communication. Accessing a memory word typically requires 1 to 10 nanoseconds. Nowadays your communication is between nanoseconds, not also milliseconds. Is nanoseconds, means just a fraction and your message is being passed. It is now common to put several processing core on a single CPU chip. So nowadays you have in Intel i3, i5, you have i7, i10 processor, on which chip processing is very faster and you do not have to hesitate for parallelly accessing the networked computers. As well as CPU. Now model of shared memory multi-computers have been implemented using physical separate CPUs. Now physical separate CPUs are being attached to a memory for parallel computing, and for which multiple cores of single CPU or a combination of the above is given as shown in the below figure. That is the first one, that is this one. Then in message passing multi-computers, that is the second scenario, B1, CPU memory pair, we are connected through high speed interconnect. Because of, see, if you have to see, this interconnect is being shown with local memory as well as CPUs. each CPU is having a separate memory unit. That means for what? Message passing. Processors have their own memory and other processor cannot access it. So this processor cannot access this memory, this processor can, means intersharing is not possible. CPU communicates by sending messages to each other over high speed interconnect. Because of this high speed interconnect, CPUs can connect to each other for sharing of memories. And we compare to multiprocessor, these are easier to build but complex to program. These are easier for connection, but to keep those data interconnected, it is very complex to maintain such data, and which is shown in this figure B. With this, it takes hardly 10 to 50 microseconds to send a message. So for here, that the first scenario, it was 1 to 10 nanoseconds. Here it is 10 to 50 microseconds. Next scenario, that is third one, is all the computers are connected over a wide area network, that is WAN, WAN, WAN. And to connect to that wide area network, that is global network such as the internet, to form a distributed system. Now when you connect globally, it can be called as a distributed system because we are joining n number of components together to one single system. Each of these has its own memory. So each of these have, if you can see the plus sign, they have a complete system connected with an internet. Nowadays we access this distributed system as well, and each of these having its own memory, and the system communicate by message passing, and because of which, see here, only communication was there over shared memory. Here CPUs were getting sharing data or connecting with each other with the help of interconnect. Here they are communicating with the help of message passing, because each of them have their own local memories and they act as a whole single complete system. And it takes 10 to 100 milliseconds, that is microseconds, to send a message. So the message passing rate here is 10 to 100 microseconds. So this is the third scenario. Next is multiprocessor hardware. So when we talk about multiprocessor hardware, there are three bus based multiprocessors. So three normal multiprocessor systems are there. What are multiprocessors? In multiprocessors, processors share the memory. So processors will share the memory as all the work is done on the processor itself. Multiprocessor OS carry out the same functions just like your operating system. So multiprocessor act like your normal operating system when they are working, but they require some unique features for process synchronization. So there are, if they want to be differentiated from the operating system, they have some multifunctional functionalities, and that is synchronization, process synchronization, resource management, and scheduling. These are the different techniques by which it differs from your normal operating system. So how is your multiprocessor hardware? So multiprocessor hardware concept illustrates the organization of hardware, their interconnection, and the manner in which it communicates with each other. So basically hardware is a concept in which how they are interconnected, how they communicate with each other, and how do they organize the hardware which is used for this communication. Multiple CPUs exist in distributed systems. So as I said that if distributed system scenario is there, multiple CPUs will be connected with each other. There are two types of multiprocessors. First one is UMA, that is Uniform Memory Access Multiprocessors, and NUMA, that is Non-Uniform Memory Access Multiprocessors. So without caching, how does it occur? With caching and private memories, it is like this. So this is the scenario for your three bus based multiprocessors. Why bus? Bus means, see here, when we are talking about bus is a single storage in which you have n number of windows, n number of seats, n number of access. Anybody can enter into it. But you have a single door and a single driver to run it. That means my bus is connected with n number of windows and n number of seats. I just can enter the bus and just access my functionality and just can move out with one door. That is the bus technology which we can say. So when I talk about UMA, that is Uniform Memory Access Multiprocessors, using crossbar switching, how do I do that? So when I say crossbar switching, my crossbar switching allows me to have number of processors and memory modules are connected by a crossbar switch. So when CPU wants to access particular memory, a cross point switch gets closed. So when my CPU wants to access a memory, if it is not available, it will get closed. If it is actually working, it will show you. So how it is shown, we'll talk about it. Several CPU can access different memories simultaneously. So it's not compulsory every time my CPU is using single memory. So this is basically CPU and this is basically memory. So when I'm talking about this, when my CPU wants to access this particular memory, so that time one has to wait. If it is actually acquired by some process, the another has to wait. That is a waiting process. Here for CPUs and n memories, n square cross point switches are required. So if n points, many cross point switches are there, that time this can be possible. The best property of crossbar switch is that it is non-blocking network. So it does not block the network, means no CPU is ever denied the connection it needs because some cross point or line is already occupied. Nothing is being denied, they are waiting, they are not going in the non-blocking stage. Cross point switch is open once the task is being done. If it is closed, it will show you like this. If it is not like this, if it is open, it will show you like this. This is the use of crossbar switch. This is normal 8 into 8 crossbar switch. There can be many opened crossbar switches also. Next is UMA multiprocessors using multi-stage switching networks. So how do you do that? Multi-staging. A 2 into 2 switch with 2 inputs and 2 outputs. So a 2 into 2 switch is this one. That is 2 inputs and 2 outputs is used to design the multiprocessor messages coming on their either input line can be diverted to either output line. That is, when I have 2 input lines, I should have 2 output lines to get out of it. So diversions is possible. Each message contains 4 parts. So every message which is entering this will have 4 parts. That is, first one is module, second one is address, third one is opcode, and fourth one is my value. Now what is that? Module is indicates which memory to be used. So whichever task is on that task, it will tell you what memory should be used. Second is address. Now address here basically means that my actual address in with the module is going to work. That is my static address, my dynamic address, depending on the memory which I am using. Opcode specify read or write operation. That is, if my process wants only reading the memory, it does not want a operational code to be writing on the memory. So I'll only provide read operation. So operations, that is read and write operations, is termed under opcode. And fourth is the actual content of my values from the module. That is the operand. That is, it can be if operand, the actual switching, moduling, all such things are there in the value. For any input in any of the 2 output line can be selected. Any memory can be accessed by any switch. So it's not compulsory that A has to go for X only. A can go for Y, B can go for X, then A can go for X, depending on the switches and values it is. So how multi-stage switching networks is possible? So multi-staging, this is 3 stages possible. That is fast switching, CPU and memory needed, and it is costly. This multi-stage switching network is costly, but rather than that, to reduce the latency means as fast as the waiting rate we can complete the task, that is more easier. These 2 into 2 switches can be organized in multiple ways. Construct larger multi-stage switching networks like omega network. So this is basically an omega network which is being sorted out to connect more and more switches at a time. To connect 4 processors to 4 memory modules, total 4 switches are used. So total 4 switches, and by 8 they are multiplied, so that 4 into 4 into 4 can be done. 3 staging can be done to increase the multiprocessing rate. In general, for n CPUs, n memories, and we need log 2n stages with n divided by 2 switches per stage for total n of 2 log 2n switches, which is a lot better than n raised to 2 cross points. So rather than creating problems in the cross switching bar, what we can do is switching networks into multi stages can be a easy possible way. Next is NUMA multiprocessor. So what are the characteristics of NUMA? There is a single address space visible to all CPUs. So one single address is there. Access to remote memory is via load and store instructions. So two instructions are there, load and store, which will be used to access a remote memory. Remote means easily accessible anywhere. Access to remote memory is slower than access to local memory. So rather than local memory, remote memory is available everywhere. So it's a bit slower than your normal memory. Next is NUMA multiprocessors. So when we talk about NUMA multiprocessors, how do they work? So if in NUMA machines, access to local memory modules is faster than access to remote ones. So these were the characteristics which I have told you. If cache is absent, then system is called NUMA, that is non-cache coherent NUMA. If cache is not available, when caches are coherent, the system is called CC, that is cache coherent NUMA. A direct based multiprocessor is well-known approach for building a large CC NUMA multiprocessor. A database containing locations of each cache line and its status is maintained. So each cache line database is being maintained when they are in the NUMA multiprocessor, that is non-uniform memory access multiprocessor. So diagrammatically, which is shown like this, that is a 256 node directory based multiprocessor with node 0, node 1 and node 255. So this is ... interconnection of networks will be there with non-memory accessible, that is a certain consistency is not maintained. It can be in variable lengths of memory accessment. How noding is being done over division of networks, that is how much nodes are there, how much blocks, offset how many are working. So this is the directory maintained of the nodes. Next is multiprocessor operating system types. So each CPU has its own operating system. This is the first one, that is partitioning a multiprocessor memory among 4 CPUs. So these are 4 CPUs which are having their own memories, private memories. They are connected with a bus and they have those datas of these all CPUs is under one memory and they have their own OS code. Then to run these CPUs, they have their own input output connected with the bus. This is the first type in the operating system. So when they say that each of them are having one CPU, so the following are the 4 aspects of this design, that is the system call issued by process is caught and handled by its own CPU. So if any system call problem is there of their own CPUs, they will be handled by their own systems. Next is using the data structures, that is the algorithm. Each operating system owns its tables and its own set of processes that schedules by itself. So each of them will have their own private scheduling tables as well as process tables. Processes belong to a particular CPU and not to all. So each processor will belong to its own zone only, not to everything. all the CPUs. That means as physical pages are not shared, any of the sharing is not done, CPU has pages to spare while other paging continuously. They will have spare pages of their own. As memory allocation is fixed, CPU cannot borrow the pages from CPU having spare. So as memory storage here is fixed, any of them cannot share their remaining spare pages to any other system here. OS maintains a buffer cache of just used disk blocks independently of other one. Consequently, a certain disk block may present and dirty in multiple buffer caches simultaneously, leading to inconsistent results. So input output is single, as because of that disk block sharing is there and disk blocks independently, but this can be because of multiple buffering, there can be a problem. This problem can be avoided by only removing the buffer. Through input output, if buffer is removed, that is prior backend processing is removed, then this problem can be solved for higher performance. So this model is hardly ever used in production systems anymore, although in the early days of multiprocessors it was used. Because of these private sharing systems, this is not preferable as much as possible, and multiprocessors are, these type of multiprocessors were used in the prior days, which is currently not that much used. With this we'll stop here. We'll continue the next topic in the next lecture. Thank you.